Well, good afternoon. It's already 12:24. I was waiting for students to show up, but so far none have. This is Wednesday, the 8th of November, 2017, and it's supposed to be Calculus 3 class. Right now, I'm the only one in the room, so let's get started where we left off last time. Let me just give you a couple of announcements, though. First, in case any of you have classes on Fridays, or if you were planning to come to school to take care of business or do research or do anything else, see an advisor, anything like that on Friday, don't, okay? Because Friday is the day before Veterans Day. Saturday is actually Veterans Day, but they're giving us Friday as a holiday, so it's a state holiday. The college will be closed. No one will be in the offices. So no office hours, no classes, no nothing. So please don't show up expecting to catch somebody on Friday. You won't, okay? After that, I don't think any of you will be around next year, but if you will and you're interested in participating with the math team, please give it a consideration because it will really hone your skills in math, though you're at pretty high level now. But if you're going to be here next fall, please consider joining the math team. Let me know or let Ms. Nyla Geraci know, and we'll get you in touch with them. And then finally, I'm trying to tell all my classes, we do have an election for the U.S. Senate coming up. The state of Alabama does, December 12th. That's just almost a month away. A little over a month away. And you still have time. If you're not registered to vote in the state of Alabama and you're eligible to vote here, you can still register. I can't remember what the exact date is. Sometime toward the end of the month is the deadline for registering. If you're going to be out of town and can't vote, there's still plenty of time to get your absentee ballot applied for. That's actually sometime, I think, in early December. But the main thing is vote. Please vote. I'm not going to tell you who to vote for or how to vote, but please do. It's a weird time for an election. Not often do we elect people in December, but sure enough, we are. This is a special election. It's the only thing on the ballot, so don't think, oh, that's not worth going to the polls for. It is. Please go. Please vote. Especially on a midterm off time like this, very few people do go out and vote, so your vote matters even stronger. So you get a better percentage of being on the winning side if you vote this time. My wife did calculations on the primaries for this Senate seat. The candidate with the most votes for the primary, either primary in this election, had 8% of the Alabama's registered voters. 8% was deciding who was going to be the candidate for that party. Fewer for the other party. So that's not a democracy. We ought to feel like you're representing the majority of the state, and there's no way to tell that if only 15% come out to vote, 20% come out to vote. Please vote. Get your vote in. You'll never have your vote count any stronger than in this election because this is, and it's really an important election. So please vote December 12th. That's a Tuesday. Vote before you come to school, as soon as you get out of school, on your way home from school, in a break between classes, whatever. Please make a point of voting between 7 a.m. and 7 p.m. on Tuesday, the 12th of December. All right, enough of that. Let's get on to today's class. Where we left off last time was example 3, kind of the middle of page 770. This is chapter 14, differentiation in several variables, 14.4, differentiability and tangent planes. So example 3 says, find the tangent plane of the graph of an, I'm going to blow it up so you can see a little better, but I can't write on it then. Okay. F of xy is equal to oh, this is not this. Oh, wait. This is a different function. Okay. It looked like this one, but it's not the same one. Let me get over to the right function. All right, there's the one. I thought that looked similar when it was real small, but when I got a closer look at it, nope, that's not right. Okay, here we go. Find the tangent plane of the graph. F of xy is equal to xy cubed plus x squared. And it says at the point 2, -2. Okay? So that's we want to find the tangent plane there. Well, what's true about the tangent plane? If you turn back one page, you'll see the tangent plane is, and as soon as I go to right, it's going to shrink, which is fine now, I guess. The tangent plane to the graph at some point is a plane of the equation z is equal to f at AB plus f sub x at AB times x minus a plus f sub y of AB, which is partial of f with respect to y, evaluated at AB times y minus b. Okay, got too extravagant with my spacing there. All right, now what do we need to calculate here? What we need to calculate is, of course, f at 2, -2. So f at 2, -2 would be, that would be 2 times a -8, that would be -16, plus, I think that's x squared, plus 4, which looks like to be a -12. Did I read that correctly? Yeah. All right. Now, next thing we have to calculate is f sub x, the partial of f with respect to x. First the xy, and that would be, goodness gracious, I think that's y cubed, and that's all, folks, okay? Because the x squared term has no y, no, I'm sorry, y cubed plus 2x, sorry, okay? So, f sub x, partial of f with respect to x at 2, -2, is what we're interested in, would be -8 plus 4, which would be -4. Okay, we also need to know what f sub y is, partial of f with respect to y at xy, and that would be 3xy squared, and that's the one that's plus 0 because there's no y dependence in the x squared term. Okay, so plugging in f sub y at 2, -2 would be 3 times 2 would be 6, times 4 would be 24. So it's increasing big time in the y direction, decreasing fairly quickly in the x direction. Let's go back to this point and see if we can make that out a little better. Okay. Boy, this is it's so hard to see 3 dimensions in 2-dimensional space. So there's your point 2, -2, -12. Okay. Now, in the x direction, x is coming out this way, y is going back that way, z is going up. In the x direction, sure enough, this looks to be going slightly downhill. The tangent line to that curve right there at point P, 2, -2, -12, would be -4. But in the y direction, and that's this way, it looks like it's going uphill. Now, it doesn't look like it's going up at a 24, so I have a feeling our scales are a little warped here, but because that didn't seem like a -4 in the x direction, and it sure doesn't seem like a plus 24, I think is what we got it at in the y direction, okay? But you can see going down in x, up in y. Okay, so now we plug in. So z is equal to -12, and I was going to put a plus, but that's actually a minus, -4 times x minus a, and your a was 2, x minus 2, plus 24 times y minus b. Your b was a -2, so that makes it a y plus 2. All right. Now we can still clean that up some. Z is equal to -12 minus 4x plus 8 plus 24y plus 48. Wow, big numbers. Okay. And combining like terms, that would be z is equal to -12. Let's see, let's do it this way. 48 minus 12 is 36, plus 8 is 44. Good deal. Good to see you here. Jasmine's here. All right, let me get adjusted here. These lights swap. Yeah, it's coming home. It's just really slow there. All right, just a couple of things. I made the announcements earlier, but since you're here, you may not go back and listen to them. You do know Friday is a holiday, right? No, you didn't. Okay. Friday is actually the day before Veterans Day. Okay. Veterans Day is the 11th, and Friday is the 10th. But since we're not going to be in school anyway on the 11th, Friday is the official state holiday for Veterans Day. So none of the offices will be open. Nobody will be here. Don't make any appointments for that day. Don't think you can come by and check something out. You can't. Nobody will be here. Okay? So that's coming up Friday. And you're not going to be here next year, right? You're graduating beforehand?
Well, I'll be next year.
Yeah, but next fall is what I mean. Yeah, right. They're looking for more people to do math team this year. Never did ask you, I think I did ask you, how was the math team visit?
It was okay. It was like a lot of stuff.
Yeah.
Right. Yeah, it was hard.
Yeah, I know it is. And that's why they want people to start practicing now for it, rather than wait until September.
Like if we would have practiced like if you went to the
right. So if you know any good math students who will be here in the fall, please encourage them to do it. Because it is a lot of fun. I think so anyway, and I think it'll help your math in your other courses that you still have to go big time. So encourage anyone to participate. All right, we're doing example 3 on page 770. This is in chapter 14, differentiation of several variables, section 14.4, differentiability in tangent planes, and that's exactly what we're doing with this problem. Okay, what it is to find the tangent plane to the surface of f of xy is equal to xy cubed plus x squared. Again, this is written so small it's hard to read. Passing through the point, over the point x equal 2, y is equal to -2. Okay, well the tangent plane given by the formula given on the previous page. And I'm trying to think if there's a good analogy to this in the in the two-coordinate system. If you're looking for, the plane, the line that's tangent to the curve, whatever the curve happens to be, y is equal to some function of x, then what we would do, the tangent line to that would be y minus y1 is equal to the slope of that tangent line times x minus x1, right? And then if you wanted to add the y1 to the other side, it would be y is equal to y1 plus slope m times x minus x1. Well, that's sort of what this is. This is z minus z1, you might say, which is alpha of AB. So z minus z1, which is the point of, so z equal alpha of AB. And then, because you don't have a slope of a plane, you have the slope of the two primary axes. In other words, the partial derivatives along each of those axes. And this would be the slope in the x direction times x minus a, plus the slope in the y direction, plus the y is AB, at x times x minus b. So you see it's a lot like, kind of like your point slope formula in a straight line. This is almost that kind of stuff in a plane. Okay? I don't know if that's helpful or not, but it helps me think of it. So, plugging in what we know, here is the function alpha of xy. We're at the point 2, negative 2. So plug in 2, negative 2 here, and you get 2 times negative 2 cubed is negative 8, so it would be negative 16, plus 2 squared, which is 4. Negative 16 plus 4 is negative 12. So that's what goes there. Alpha of AB is minus 12. F sub x of AB, you first do the partial of f with respect to x of this function at xy, and that would be y cubed, because the x is to the first power, so you just count the y cubed as if it's a constant times a linear thing, so that would just be the number. Then the derivative of x squared would be 2x. Plug in there, x equals 2, y is equal to negative 2. And again, you get negative 8 here, and plus 2 times 2 is 4, negative 8 plus 4 is negative 4. So there's your F sub x at AB, and there's your negative 4 there. Times x minus a, where your a is 2. So x minus 2. Plus, now we need the F sub y at AB, so I moved up here to do this one. The partial of F with respect to y of this function here, y cubed plus x squared. The only term with y in it is the first one, the partial of that. The derivative of that with respect to y would be 3xy squared. 3xy squared. Plug in x equals 2, y is equal to negative 2, so F sub y at 2, negative 2 would be 3 times 2, which would be 6, times negative 2 squared, which would be 4. 6 out of 4 is 24. Okay? And, by the way, and I tried to do this, of course, talking about it. I had the picture there, but it's still not easy to see. Here is that surface. Now, this surface is at 2 on the x-axis. Here's the x-axis here, positive x-axis here. Minus 2 on the y. There's positive y. Minus 2 on the y-axis. So 2 this way, minus 2 this way. There's a point, and then you go up, or I'm sorry, down 12, minus 12, okay? Down 12, okay? So here's the origin up here. It's down here somewhere, okay? Down 12 on the z, okay? Now your partial of f with respect to x at that point was negative 4. Well, along the x-axis, it sure enough seems like it's going downhill there. Now that doesn't seem to be steep enough to be a minus 4, but I have a feeling the scale is a little off here, okay? And then in the y direction, it's the slope of this curve here that's parallel to the y-axis here at that point, and that would be, it sure doesn't look like a plus 24 to me, but it's certainly positive. And again, I have a feeling the z scale must be compressed compared to x and y. Because that sure doesn't seem like minus 12 down if this is plus 2 and that's minus 2. I mean, the z is really compressed. So I think that's why it looks a little bizarre here for that. But you tell it's down and up. Okay, greater up than down. It's just the numbers don't quite fit. So anyway, you plug that in, 24 for f sub y, and then y minus b. Well, your b is a negative 2, so y minus a minus 2 is y plus 2. Okay, so then I distributed minus 4 across this one, minus 4x plus 8, and then distributed 24 across that parentheses, plus 24y plus 48. What I was about to do, right when you came in, was I was combining like terms. Okay? And what we have here is minus 12 plus 8 would be minus 4, plus 48 would be positive 44. So that's where the 44 came from. Minus 4x plus 24y. Now, you can write it like that. You can move it around some and say 4x minus 24y plus z is equal to 44. There's another expression of it. So I don't care how you write it. Either one of those are legitimate points. Let's see how the book did it. They kept it in 44 minus 4x plus 24y. Okay. Find the tangent plane to the graph at that point. Okay, we did it. All right. Now, the next little topic here is, by definition, if f of xy is differentiable at AB, then it is locally linear, and the linear approximation at, at AB. Sorry, this is on page 770. Okay, just the bottom third of the page, approximately. Linear approximation and differentials. Okay, so here, let's see, I don't think it's quite here yet. But I'll go to this page, and before we get to it, in fact, they go through. Let me lead up to this one. Okay. F of xy is approximately equal to f of AB. That gives you a point to start from. Where are you starting your z from? Okay. Plus f sub x at AB times x minus a plus f sub y at AB times x minus y. I mean, y minus b, sorry. All right. Now, if you're saying, hey, doesn't that look almost exactly like your tangent plane? If f of xy is z, that's exactly the formula we had for the tangent plane. Okay? Well, what we're saying here is that tangent plane is a good linear approximation. Let's go back to that curve, which was not a particularly great curve, okay, to do from. If you draw the plane there at that curve, anywhere around that point AB, okay, plus 2 minus 2, y z is equal to minus 12, anywhere around there, you're fairly close to being on a plane. So therefore, that is a great linear approximation for points close to AB. Okay? So nothing too new here. It's what we were just doing. Your function of AB is a little bit off, but not too far from the linearization of AB, which is your tangent plane, okay, for any xy at AB. And that's exactly what it's saying. This is your f of xy, anywhere close to AB, it'll be f of AB plus taking off and going in the direction of your partial derivative there, which is sort of the slope in the x way, times x minus AB. How far off you are from AB, that tells you how far off this approximation is. And then this one tells you how far off your y is. This is a y minus. That's a pretty ugly looking y. Let's see if we can clean that up just a tad. Okay, still not too clean. Okay, let me see if I can get that better a little bit. How far off from AB or B the y is, okay? F of y at AB tells you what direction that's going, and y minus B is how far off you are, so that would give you a good adjustment there, and that's approximately what that's your linear approximation. Okay. So your f of xy is approximately equal to that linear approximation, which would give you a plane there for xy close to AB. How close is close enough? It is hard to say. All right. Now I can't read these because they're so terribly tiny. Now you may think looking at that they're not that bad, but looking at this they're even worse. Okay. So if we go, okay, here's the point AB, x equal a, y equal b. Okay, you go a little bit further along x, h over here, b a little bit further along y, that's your k there. But that's going to be approximately whatever your f of AB was to begin with, that's where you're starting point, plus this is your delta x now, so it's plus f of x at AB, the first derivative, a partial derivative of alpha at x, alpha with respect to x. Sorry, I'm about to sneeze. Oh my goodness. Partial of alpha with respect to x at AB, that's just sort of the slope of it there, times your change of x, which is your h, plus your change of y, that was going up this way, and y at AB times your change of y. That's your k. So this viewpoint there, a little bit off from where, h away from A, k away from B, that gives you about what the value would be at there. It's an approximation. It's not exact. That's why the wavy equal sign is there. Okay? Now, here's another way to look at the same picture. Okay. Your difference in the F, okay? In other words, F of x, f of AB is where you're starting, and how much is F changed when you go x plus h and y plus k? A little bit off from that, a new point. That is your difference here. Now this is the difference of f of x plus delta x, y plus delta y, which is x plus h and y plus k. The difference of that in the actual F of AB where you started is approximately this. Partial of F with respect to x times the change of x times partial of F with respect to y of A at AB with the change of y. Which basically is the same thing you had before. It's just that the F of AB you had in front here, you subtracted it from the F of xy here. That gave you your delta x. So you use that same formula now about 3 or 4 different times, okay? And that's how that. Now that's your delta F written in differential form. Whereas before, you know, you would this would kind of be represented by the slope. So this is the change of y would be the slope times the change of x. So if you knew your slope and knew how much x changed, that would be a good approximation for how much the y had changed. Now we're in 3 dimensions, so that's how much the z has changed when you change a little bit in x, a little bit differently in y. That would give you an approximation for what your change of f or z would be. All right. That's almost what we call a differential form. Here is kind of sorry. My eyes are just as dry as they can be. Did I blow this up? I don't think so. Okay. All right. This is changing the deltas we had in the previous equation to the d's we have in this equation. So df, change of f, incremental change in f, is your partial of f with respect to x at xy times the change of x plus the partial that you had of f with respect to y evaluated at xy times the change of y. In the previous one, this was delta x, this was delta x, and delta L to delta x, and delta y. Now this. Well, if you go back to what this was, this is partial of L with respect to x, there's L sub x is, partial of L with respect to y is this one, and you see it does look like the change of L is the change of L, okay? And that's exactly what it is. Okay. Okay. Just looking at my book, I doubt if there are any other formulas highlighted that don't seem to be here. I think what we do next, if I'm not mistaken, this probably is, no it is, I was thinking this next, this is the figure that, sorry. Okay. Okay. Now, all right, just to get an idea. Here's your surface. The blue sheet there, 3-dimensional sheet, is your surface. F of xy. Z is equal to F of xy. Okay, here's the point in question. No, here's the point in question. No, that is what I said the first time, is the point in question. That's your, yeah, that's the tangent, where the tangent plane touches. So that's your xy, or you might call it your, I'll give the xy axis, but the AB, okay? That's your AB, and this is your Z at AB. That's where the tangent plane touches. That's where it's tangent to. All right. Now, somewhere else here, this is your function, f of xy. There's your linearization at xy, based on the partial of f with respect to x and partial of f with respect to y. You know, and you change there. These are pretty significant looking changes here. So you do get changes in your z value because of that. Here it's touching, there it's not, so you do have an error there. Okay, the plane is the linearization, the f of xy is the function itself. So the quantity df really don't care for this rendition very much at all. Okay. It's sort of hard to follow what they're talking about. But here's your f at AB. Here's your f of some different xy. Okay? These are actually your function on the blue sheet. Now, this up here is not your function on the blue sheet, but it's based on that. That's the linearization. So it's up here. Now, all these are reference to the z-axis, not to the x and y. The x and y axis, this would be an x and that would be a y. Well, I mean, they don't even show where your axes are, so it's sort of hard to tell. It looks like you got an x, y, z orientation. Positive x going back into the board, positive y going that way, positive z, of course, is up. And if you're going from this point to this point on the curve, there's these points down here. And it's indicating the x is going this way, basically, and the y, I don't know. It looks like the y is now going that way. That wouldn't be a right-hand rule, but anyway, they're trying to represent that well. That's where I think they fall apart a little bit. And then your they're calling this your df here, whereas this is your delta f. This is the actual change of the function from this point to this point. They're saying the df is the change of your function value still. I'm sure what they have is right, but it just doesn't look like it. Okay. But anyway, again, I don't find this illustration to be particularly enlightening. It's almost more confusing than it's enlightening. I can understand the formulas. They make sense. The pictorial representation of them, I have more problem with that. Okay? Now, whether you do or not, let's move on to, whoa, we won't move on. Let's do example 4, and then we'll do example 5, and we'll be through. Okay? Do we have a slide with more space? Yeah, this has more space than the previous one, so let's do this. Use the linear approximation to estimate 3.99 cubed times 1.01 to the 4th power times 1.98 to the -1 power. Okay. Goodness, I'm getting cold again. How are you? You are cold. Okay. Now that it's turned cold outside, I can't even open the windows that help because it's probably colder out than it is in now. But not by much. This is pretty chilly in here. Okay. Says use a linear approximation to estimate this. Okay? What I would do first is write this down as a function and name variables. So this would be f of x, y, and z. So hang up drawing a picture of this one, because this is three-dimensional surface, enclosure, and you're looking at some fourth dimension that we can't draw, okay? That's your F is your fourth dimension here, okay? And let's just call this, A to the third, B to the fourth, over, you could put it over or times C to the minus 1. Okay. All right. I was going to try to make it without doing this today, but I don't think I can. I've got to go clear my head. Sorry about that. All right. Let me change these to X, Y, Z. Okay. X cubed, Y to the fourth, Z to the minus 1. The product of those powers and stuff is going to be what we're looking for. That's the value we're looking for. Or at least a linear approximation to the value. That's what it says, right? Or use the linear approximation to estimate that. All right. Now, what I was thinking, your A here that represents the X is basically 4, right? Your delta X is a minus 0.01, right? Your B that represents your Y is 1, but your delta Y is 0.01, positive 0.01. And your Z, C that would represent Z, or the value that you're going to be evaluating at, is 2, with the delta Z being negative 0.02, right? So that would be what you're representing here, okay? Now your exact value would be, you can get your calculator and do it, 3.99 cubed times 1.01 to the fourth over 1.98, okay? That's the exact value, okay? Now, you can plug that in if you wanted to, okay? But what you're going to have, your A is going to be 4. This is why I was putting the A, B, and C there, but it's better to start with the variables. Your B is going to be 1, and your C is going to be 2, okay? Now you have a, I don't know, do they call it delta X or they just don't say, yeah, delta X, okay. Your delta X here, and that delta X is negative 0.01, okay. Your delta Y here, and that is positive 0.01, and your delta Z here, and that is negative 0.02. Okay, that's your delta values there. Now, like I said, you can just plug that in, you get exactly what your F is, okay, the actual function. But we're wanting to do the linear approximation of that. So, what we'll do then is do our F of ABC, where the A is the approximate values, okay, plus partial of F with respect to X at ABC times X minus A, plus the partial of alpha with respect to y at A, B, C times x minus y, y minus b, okay, plus your partial of z with respect to alpha with respect to z at A, B, C times your z minus c. Okay. Now, that is going to be the linear approximation to it. Seems like a lot of work to get an approximation. You just plug it in and get the real value, but it's not too really all that bad. Okay? So let's first do our alpha of A, B, C. That would be 4 cubed times 1 to the 4th times over 2. Okay? That's not too bad to do. 4 cubed is 16. No, I mean 64 times 1 and divided by 2. So, let's say 64 divided by 2 is 32. So that's your starting value. Okay? That's where your 4, 1, 2 would be. And we're going to deviate from that just a little bit. So let's do your f sub x. Okay? Well, what is your f sub x? I'm sorry? Okay. It is when you plug in your ABC, which is 4, 1, 2. See, those are the easy to calculate ones, right? 4, 1, 2. Okay. So when you plug that in, you get 4 cubed times 1 to the 4th of 1 divided by 2. 2 to the minus 1, 2 divided by 2. So that would be 64 divided by 2 is 32. All right, let's do the f sub x. Well, let's first find that with respect to x, y, and z, that's 3x squared y fourth z to the minus 1, right? 3x squared y fourth z to the minus 1. You keep the other two variables constant. Only one you're taking respect to, you do. Okay. And this thing at the value 412, okay, that would be 3 times 16 times 1 over 2. Okay? So that would be 3 times 8 would be 24. Okay, so that's your partial of alpha with respect to x at that point. That's not at the actual value, but at that point. Okay? So you start with the alpha of ABC, which is 32, plus, here's your 24, alpha sub x at ABC, times x minus a. Well, that's x minus 4. Okay? Okay? Now, we'll come back to that in a minute. Let's do our alpha sub y at 4, 1, 2. Okay? Partial of alpha with respect to y would be 4 x cubed y cubed z to the minus 1. Right? You only take the partial with respect to y. The only y dependence is the y fourth. So that would be 3y cubed, but it's 3 times x cubed y cubed z to the minus 1. And plug in those values, and that would be, I shouldn't have put the 4, 1, 2 there. That was x, y, z. Now when you plug in those, that gives you 4 times 64 times 1 divided by 2. Okay, 4 times 64 is 256, right? divided by 2 is 128. I hope. Yep, that's it. All right, we also are going to need, okay, I'm going to go and write that part in. So that's plus 128 times y minus 1. Okay? Because your b is 1. All right, let's do the f sub z. Okay, I'm just going to leave off the parentheses. We've done enough of that. Here's your f. Partial of that with respect to z would be a minus x cubed y fourth. Now you'll have z to the minus 2, right? So that's over z squared. So it's going to be a negative, and 4 cubed is 64. 1/4 is 1, okay? And 2 squared is 4. So this is going to be 16. Negative 16. All right. I don't know where my negative went. I set it, I pressed the pen to the paper, but nothing showed up. Okay. There, I did it stronger. So here, that will then be a minus 16 times z minus c, z minus 2. Okay. Now, if it's all right, I'm going to erase some stuff. Is that okay? Huh? Okay. And I'm hoping I don't erase something I'll need again. I sure don't think I'll need this any longer. I've already calculated that. Okay. Done my f sub x and plugged in, so I don't think I need either of those again. I've done my f sub y and plugged in. I don't think I need those anymore. And that may give me enough room, so I'll hold off erasing any more in case I need it. Okay. Okay. So this linear approximation of f would then be this thing. All right, I'm sorry. They're not doing the x minus 4s here. I'm sorry, I'd forgotten. Goodness, where is my... There we go. Hit the wrong key. All right. This should not be x minus a and x, y minus b. This should just be our delta x's, delta y and delta z. That would have made it a lot easier to write, too. This is delta x, this is delta y, this is delta z. Okay? So let me change them down here, too. Okay. Okay. Now what is the delta x? I wrote them up here. Delta x is negative 0.01. Negative 0.01. Okay? Your delta y was a positive 0.01. And your delta z was a negative 0.02. Okay. Why did I leave the delta z in there? Okay. why do I have a minus 16 there? I don't. It's the what? The what? Oh. Oh, I see. Okay, yeah. Okay, I got off a line here. All right. Got it. That was a minus 16 too, wasn't it? Okay, let me change that back to a minus. Yeah, there we had it. Minus 16 times your delta z. Oh, I know. Okay. It was driving me nuts here. It's plus f sub z at a, b, c, delta z. That's what should have been there. And now filling that in, minus 16 times negative 0.02. Okay? So what does this come up being? 32. That's what it was at 412. 412. That's what the value was. We could do that one. And then here we do minus a 0.24 plus a 1.28 minus a 0.32. Okay? Well, not going to be a lot of change here. Add the two minuses together, you get negative 56.56, and add that to 1.28, that would be a 0.72, I think. So that would be 33.72. That's your linear approximation, 33.72. No, it isn't. 32.36. I knew I shouldn't be doing this in my head. Okay. Let me try that one more time. Minus 0.24 plus 1.28 minus. Oh. That's a plus here. Yeah, because it was minus and a minus. Okay. That's where I messed up. It's a minus 16 and a minus 0.02. So that turned into a plus. And that's a plus 0.32. All right, now we add the pluses together. That gives me a 1.6 minus 0.24. That would be a positive 1. Yeah. Is what? 33.36. Yeah. 33.36. Yeah, that's what I was just getting here. 1.36. Add that to that and you get out 33.36. Okay? So that was your approximation. Now, also, since you got your calculator out, actually do that calculation at the top. 3.99 cubed times 1.01 to the fourth times 1.9 divided by 1.98. Yeah, times 1.01 to the fourth, and then rather than do it as minus 1, just divide it by 1.98. Okay, 33.38 you said? Yep, that's what they got too. Okay. Now what we want is the percentage. Okay, so this is 33.38. We got 33.36. Not bad at all. Okay. So what is your percent error? Let's see. All right. How we define percent error is equal to the actual error divided by the actual value. What is the actual error? Okay? The actual error is the difference between your measured and your actual. Where and they do absolute difference, so it doesn't matter which one you do. That's 0.02, because the difference between your estimated and your actual is 0.02. So that's 0.02 divided by your actual, and the actual was 33.38. Okay? So you do that and you come up with an incredibly small number. Move the decimal 2 places to make it a percent. So 0.02 divided by 33.38. Is 0.02. Okay, divided by. Say that again.
5.992.
Okay. Well, they got 0.00075. 0.02 divided by 33.38. Let me see if I can't get out of this without turning off Screencast-O-Matic. So I just don't have a calculator here. Huh?
I looked
Yeah.
at my real calculator in my car.
Yeah.
But I did come here and said 5.99 times 10 to the negative 4.
Wow. Times 10 to the negative 4. Well, that part seems about right. They said it was 0.075%, which is so incredibly tiny. These are both right within the ballpark. Okay. Yeah, I didn't bring a phone up here either.
Yeah, like that on my phone, 0.00599.
There.
And so it's 0.06 divided by 33.38, right?
0.02 divided by 33.38. I don't know how they got 0.00075. You got 0.00059, right? Yeah. Well, it's so small, it really doesn't matter much. Okay. Any questions on that one? All right. Let's go erase all that then and go to body mass index. A person's body mass index, BMI, and they abbreviate it just I, is equal to their weight divided by the height squared. Okay? Say again? It's body mass index. Okay. Okay. Where weight is the body weight in kilograms, which as a physicist that just drives me crazy. Weight is not kilograms, that's mass. So that's why they call it body mass index. It's not body weight index, it's body mass index. So it should be M over H squared, where M is the weight, is the mass in kilograms, and H is the body height in meters. So that's going to be some fractional form of the meter. Okay? Now, estimate the change in a child's BMI. Now we're looking for a change in the child's BMI if the weight, mass, and the height changes from 40. So we're going from 40 kilograms at 1.45 meters to 41.5 kilograms at 1.47 meters. Okay. Now, it's asking for the change in the child's BMI. And I'm asking for the actual value of it, the change in the child's BMI. So basically what you're looking for now is your delta F. Okay? Or delta I would be the better way to say it. Where, and this is an approximation, this is approximately equal to the I sub I don't like W, it's mass. So I'm going to change that to mass. I'm sorry. It just drives me nuts that they would use, okay, this is mass. It's body mass index, not body weight index. So it's I sub M times your change of M plus the I sub H times your change of height. Okay? Now, what you're going to be doing here is calculating I sub M, or partial of I with respect to M. And what would that be? Yeah, and there's your I formula up here. H squared. Exactly. So it's 1 over H squared. Okay? And the partial of I with respect to H. Ew. Let me rewrite this to be M times H to the minus 2. I prefer taking derivatives when you've got exponents rather than denominators. You okay with that? Okay. So what would di dh be then? Negative 2 m h to the negative 3. Perfect. Okay? So, let's calculate them. Okay? Now, the h that you use and the m that you use is your original, not the new, the original. So we'll use 40 and 1.45. So this is 1 over 1.45 squared. Okay? And this is minus 2 times 40. Yuck. I can't write. All right, goodness gracious. Minus 2 times 40 times or over 1.45 cubed. Okay. All right. Now what do you get for the first one? 1 over 1.45 squared. 1.45 squared. Say again. 47. Okay? And what you get with negative 80 over 1.45 cubed. .26, is that what you said? Point what? .24? Okay. Now, it's the I sub m times your delta m. Your m increased by 1.5. Right? It went from 40 to 41.5. So that's your delta m. Okay? We're plugging in here. This was this value. The delta m was the difference between 40 and 41.5. That's 1.5. No. Yeah, okay. Yeah. Okay. And then your I sub h, that's what this was. Okay. Times, what did your height change be? 0.02. What is the what?
The .47 is the
Oh, I thought you just gave it to me. 1 over 1.45.
I'm saying what you said. The B.
Oh,
That's the B.
that is your I sub m. That is your partial of I with respect to mass. Now they use weight, so I'm using mass. Okay, yeah. That's what we calculated. Hey, you're early, huh?
Yeah.
Okay.
Sorry for interrupting.
No problem. Yeah, there's probably a class next door. Okay. So, 0.47 times 1.5 minus 26.24 times 0.02. And what does that give? Yeah. That's with the subtraction, or is that just the? Okay, now it's 0.47 times 1.5 minus 26.4 times 0.02. It's all one calculation. It's from the one up there. How much the index has changed. So, 0.181. Sounds fairly reasonable. 0.181. That would be the change in the body mass index. It went up a little bit, okay, because that was a reasonable increase in mass and a little bit less increase in height. So yeah, the body mass index went up a little bit. Now, if you want to do the exact, you just do plug them in, okay? So if you plug in 40 divided by 1.45 squared, that was the original body mass index. 40 divided by 1.45 squared. 19 point what?
Oh,
02. Okay. And your I final was 41.5 divided by 1.47 squared. 41.5 divided by 1.47 squared.
point.
19.20. Is that what you said? So the difference, the actual difference in body mass index, the delta I actually was 0.18. And we estimated 0.181. That's pretty good. Okay? Do you see?
So what did you multiply for out of the initial?
Oh. The initial was when you put body mass index is 40 divided by 1.45 squared. And your final was 41.5 divided by 1.47 squared. And that gave you these two, so it went up by 0.18. Our estimate was it went up by 0.181. That is really, really close. Now, what I can't figure out, just glancing at the book, now here's one thing. They said the 1 over 1.45 squared was 0.48, and you said 0.47. Go back and do that one more time.
Well, it was 0.475.
Oh, okay, so they rounded to 0.48. Okay. So that's where they got 0.2, I guess. Yeah. They said they just rounded to 0.2. All ours rounded to 0.2, so it really doesn't matter. All right, so that finishes 14.4. Okay? Let's look at the preliminary questions. How does the linearization of f of x at a b define? How is the linearization of f of xy at a b defined? Well, it's basically that equation for the plane. F of AB plus f sub x at AB times x minus a plus x f sub y at AB times y minus b. Okay? Something like that. Let's see. This is 14.4 preliminary question. F of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Yeah, exactly. Number 2, define local linearity for functions of two variables. Okay? I don't know. I mean, I don't know what they mean by define it. It basically means the closer you get to the point, and blow up the things, the closer it is to it looks flatter and flatter. Okay? So I don't know. Do they have an answer in the back? I don't know. 2, f is locally linear at AB if f sub xy is equal to L of xy plus E of xy, where E satisfies it's the error function. So to me, you can just go back and write that from the book. But it wasn't anything to do. So in exercises 3 through 5, assume the following. Okay? So let's erase all the ink. Here's our assumptions. F of 2, 3 is equal to 8. Okay? F sub x at 2, 3 is equal to 5. And F sub y at 2, 3 is equal to 7. Okay? We're going to assume that in these problems. Goodness gracious. I feel almost dizzy. And actually, I don't know. Yesterday, it was so bizarre. Right as I was finishing eating lunch, I was drinking the last of my water, and just tilting my head back drinking, I felt so dizzy, I thought I was going to fall out of the chair. I was sitting down, and I felt like the best thing I can guess is how people feel when they have vertigo. I've never had that before, but I really felt like, I don't think I could stand up now and not fall down. You know, I felt that dizzy. And just when I stretched just then, I felt just a little bit of that, not the same. I don't know what's going on. I don't know if I'm getting a headache, something's in my inner ear. Sinus something and it's in my inner ear. I do not understand what's going on. Okay. Example 3 says, which of A or B is the linearization of F at 2, 3? What we're looking for is linearization of F at 2, 3. Okay? And here's what they say. A is L of xy is equal to 8 plus 5x plus 7y. Do you think that's the linearization of F at 2, 3? Or, let's go and do the B. The linearization at xy would be 8, that part agrees, plus 5 times x minus 2 plus 7 times y minus 3. Which of those you think is the linearization of F at 2, 3? A or B? Yes, it is B. Okay. Yeah, you got to have the change of y in there. Okay, the change of x and change of y in there. That better be B. It is. Good for them. They got it right. Okay. Number 4. Same assumptions here. This was 3. Here it's 4. Estimate f of 2, 3.1. F of 2, 3.1. Okay. Basically this, F at blah, 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 is equal to F at AB plus F sub x at AB times x minus A plus F sub y at AB times y minus B. Okay? Or something like that. actually, for the change of f, you would put delta x and delta y. So let me go back and change that. Okay. This would be delta x, this would be delta y. Okay. Well, they told us what f of 23 is, and that's 8. Plus, now if you did this, that would be 5 times the change of x is 0. So, nothing changes with that one. Plus f of y, which was 7 at AB, okay, times your delta y. What did your y change by? It went from 3, 0.1. So that would be 8 plus 0.7, so that would be 8.7. Right? Okay. Yeah, okay. Let's see what we have in the back. The B part here. Yeah, I mean, 4A, the first part of A is 8.7. Oh, that's 4. Okay. 5. This time we're estimating delta F. Okay. Okay. And your delta F at 2,3. Okay. If the delta X is negative 0.3, I don't know why I put parentheses around it. Okay. And the delta Y is equal to 0.2. Okay. So in this case, delta F is equal to F sub X delta X plus F sub Y delta Y. Just that. I mean, how much is F changing for any change of X times the delta X? How much is F changing for any change of Y times delta Y? Okay? So that would be F sub X was 5 times negative 0.3, right? That's what we told you it was, plus 7 times 0.2. Okay, so this would be negative 1.5 plus 1.4 equal negative 0.1. Right? That doesn't change by much. Negative 0.1. Good for them. All right, and number 6. Which theorem allows us to conclude that f of xy is equal to x cubed y 8 is differentiable? Which theorem allows us to conclude that? Beats me. Power theorem? I mean, I don't know what. It's sure not one we had here, I don't think, because I don't think we had it. Criterion for differentiable. Oh, I guess that's it. Theorem 2. Yeah, I guess it's theorem 2. Criterion for differentiability. If f sub x of xy and f sub y of the xy exist and are continuous on an open disk, then that is differentiable. So yeah, I guess that's it. So, I don't know what they say in the back. Theorem 2, or do they write it out? Criterion for differentiability. So they write the name of it. All right. That finishes the preliminary questions. Let's do the exercises or talk about them. Do number 1. Do any of the odds 3 through 9. Do any of the odds 11 through 21. Do any of the odds 23 to 27. My throat hurts. Do 29. Do either 31 or 33, or both if you choose. And then do any of the odds 35 to 39. All right, good deal. Any questions on... Oh, wait. We just went over a minute. We went over 6 minutes. Sorry about that. All right, we'll start next time on 14.5. Okay. Man, I hadn't looked at the clock. I mean, last time I looked at it, we had plenty of time. We just got on a roll there.